So in this video I'll be showing you how you can build your very own handheld induction gun. So you might be wondering to yourself, what is the purpose of a handheld induction gun? Can it cook me a potato? No, can't do that. How about untangle those infuriating earbuds that always seem to get knotted in a million different ways? No, can't do that. What about cook you an egg for breakfast? Well, actually it can do that, but that's not its purpose either. The purpose of a handheld induction gun like this is to heat up small metal components, and I'll give you an example where this might be invaluable. You might be a mechanic working on a car. The car's got a seized bolt in a location where you can't use an open flame for risk of melting or setting fire to other components, and we can just put the head of the bolt inside the coil of this induction gun and heat it up to over 400 degrees Celsius in a matter of only 60 seconds, and that allows us to extract the bolt far easier. So as usual, there will be links in the video's description and information about all the parts I've used here, as well as a wiring diagram which you can use to understand how everything's wired together. I'm not going to go over in great detail of all the wiring throughout the video because that diagram does a really good job of explaining everything. So let's get started. So first I'm going to remove the induction coil from the induction heater. Set that aside, we won't be needing that for a while. And we need to consider when mounting the components in our enclosure about keeping all the components cool. So you'll see the induction heater has quite a big computer fan on it to keep the heat sinks cool, and the power supply has a fan at the back here, and this fan exhausts hot air out. So for mounting, most switch mode power supplies come with pre-drilled holes that are usually tapped for M4 thread. So I'm going to drill holes in the bottom of the enclosure to mount the power supply in that orientation, and the induction heater has the M3 standoff similar to a computer style standoff, and as I said, they're tapped for M3 thread. So I'm going to drill holes in my enclosure and mount the components like so. I'm going to add to my enclosure an IEC socket so that I can remove the power cable, the mains power cable that goes to the power supply, and this IEC socket also has an inbuilt fuse which is really handy. Don't forget to add some heat shrink before making the connections. So now I'm going to mount the induction heater inside the enclosure, and I've just got some tiny 8mm long M3 screws to do that. So now I'm going to make up some cables, and I've just bought some appropriate sized spade connectors that fit onto the relay. Then for some extra street credit, you can heat shrink on some heat shrink tubing, and it helps support the connection as well. So now let's take a look at the power supply I've got here. So we've got the label here. So the first three connections are for live, neutral and earth. The next three are all in parallel. These are all the negative 24 volt output, and then the last three over here are all in parallel, and they're the positive output of the power supply. So I've made up a couple cables to the correct length. I'm going to start with the positive connection. Now I split the 8 gauge wire into two halves and then twist them, and then I can kind of sit my screw in between the two halves and then screw everything down into the power supply. Now it is important not to solder the wire if they go into a screw down style connector like this, because the solder can actually mean that the wire doesn't compress when you apply pressure with the screw, and it doesn't make a very good connection. So don't think tinning the connections is the right thing to do in this case. Now for the more eagle-eyed viewer, you might have noticed a potential problem. The power supply outputs 24 volts, but my relay is only rated for 12 volts, or at least the coil is. Now this problem can be omitted by, in the first place, buying a 24 volt relay. However, I couldn't get any locally, so this is a case of running whatever I've brought. To get around this problem, I'm going to use a very cheap buck converter. These are great for adjusting whatever voltage you need, really. So this is going to take the 24 volts from the power supply, and we can adjust it with this little potentiometer to output whatever voltage we need, so in this case 12 volts, so that our relay will run quite happily. And while you're wiring in your power supply, just add a couple of light duty cables. These only need to be rated to handle maybe an amp, and then we'll wire in our buck converter into those. So I've just mounted my buck converter into the enclosure, and if you have a look printed on the PCB, you've got in plus, in minus, and then your output plus and minus on the other side. So now I'm just going to solder on my positive and negative wires. So I've turned on my power supply, and I've got my multimeter reading DC volts, and it's on the output of my buck converter, and as you can see we're putting out 14.3 volts. So if I just use a tiny screwdriver and turn the potentiometer, you'll see the voltage is going down, and I'm just going to stop it when it's near enough to 12 volts. That'll do us right there. So now we're looking at the underside of the top of the enclosure, and we need to mount a few components in here. I've got a couple of cable glands that have got to be mounted side by side. That's for the 8 gauge cables that go out of the enclosure to the coil. A switch, and it's an on-off style, not a momentary, and a bezel for a 5mm LED. So now I'm just going to drill some holes in the lid. So next I'm going to install the power indicator LED, and I'm using this LED to show when the induction heater is powered up. So I'm just going to install the LED into the LED bezel. I'm going to trim the leads a little bit shorter, and I'm going to solder on a 1 kilo ohm resistor onto the LED. So here we're looking at the output of the induction heater, and if you remember, our copper coil was connected to these two terminals, but I'm not going to use those. I'm going to wire in my 8 gauge cable into these screw down terminals that you can see here. In my case, you can see I'm using black and red wire, but if you notice, there's no markings to indicate on the output what's positive or negative, and if you're wondering why, that's because this puts out AC, alternating current, so really there is no positive or negative. So now let's turn our attention to the business end of this induction heater. So here we've got the factory coil that came with our heater module, and you know, we don't just want to duct tape our 8 gauge cable to the end and hold on to that while something's been heated up. We want a bit of distance between our hand and the heating action. So this is my solution. So I've 3D printed a handle on my 3D printer. There will be a link in the video's description for this part if you want to print it yourself. If you don't have a printer, you could get someone, a third party, to print it for you. There's plenty of services out there these days for 3D printing. And how this works is I'm going to epoxy in these cable glands at the back. So if you imagine our two cables from the induction heater coming in the back here. And bear with me because I'm going to use an imperial measurement here because that's all they had. This is 1/2 inch, oh I know, I hate it too, 1/2 inch aluminium square stock, and it's got a hole drilled out at each end. One end accepts the 8 gauge cable and the other end accepts the heater coil. And then I've tapped out the 3 holes on the top for M4 thread. And I have a grub screw on the back, a countersunk which secures when the square stock's installed. That lines up with that hole, and then a countersunk screw goes in to stop it coming out, and then the last cap screw on the end there clamps down on the coil and holds the coil securely. So that's my solution for this job. Alright, so now I've got those epoxied in, I'm just going to feed in the cables through the back of the gun. Here's a little trick I've learned over time. When you're stripping heavy gauge cable like this, when you cut off the insulation like I'm doing now, rather than simply pulling that off and then twisting the wires, while the insulation is still on there, just twist the bit you've cut off, and then when you pull it off, the wire's all nicely twisted and it's done tighter than you could do just with your fingers. So now I've got my grub screw on one end here, and I'm just going to insert the cable into the aluminium block and then tighten down this grub screw. So now I'm just going to install this cable sleeve over the 2 8 gauge cables. So let's take a moment to look at the coil that came with my induction heater, and I'll just temporarily install it in the handle. And if you imagine for a moment this bolt is seized and it's on an engine block and it's not in an easy place to get to. If we were in a tight space, you can see the coil is not orientated in a manner that allows us to get the coil around the head of the bolt. We'd have to come at it sideways like this, and that's not ideal. So I want to modify the coil so that the coil sits in parallel with the handle, and therefore we can get the coil around any bolts that may need busting. Now this next step isn't essential, but it does make your life a bit easier if you're trying to bend copper. Over time, copper work hardens. Even if it's just sitting on a shelf for years and you're not bending it or doing anything with it, it still gets harder and harder to bend over time. And for copper, this is quite resistant. Like, I have to put in a lot of effort to try and bend this. and we can make the copper really easy to bend by heating it and then quenching it in water. So I've just got an LPG torch that I'm going to use to heat up the coil. And now the copper I can just bend just with one finger, piece of cake. So after spending maybe 5 minutes, I've managed to get the coil into the desired shape that I want. And one thing I did, which is up to you whether you can be bothered doing it, is I've made the coil a little bit smaller in diameter. And once the coil's heat treated, it's quite easy just to twist the coil, sort of wind it like a clock spring, and then that shrinks the diameter down a bit. It's quite handy too, because then you gain a bit of length. In the end you can undo sort of half a turn or a turn, and you've got enough down here to connect up the gun. So the next thing I want to do is cover the copper coil in fiberglass sleeving. This works good as an electrical insulator, because if you imagine if we're using this down in an engine bay and we short 2 of the turns or 3 of the turns or whatever on a bolt or a bit of metal, the electricity is not going to go around the coil, it's going to just arc across the bolt, and we don't want that. So we can solve that by adding some fiberglass sleeving. So now I can simply install the coil on the end of my handle, do up the cap screws to secure the coil in the gun, or the handle rather. Right, let's go give it a try. I've got an M8 bolt being held in my vise here. I've got my phone that's showing a stopwatch, so we'll heat the bolt up for about a minute, give or take. And then I've got an infrared thermometer to measure the temperature when we're done. So we're starting at 69 Fahrenheit or 20.6 Celsius. Alright, I'll just turn my induction heater on, hit start. Alright, that's a minute. 424.2 Celsius or 795.5 Fahrenheit. Pretty toasty. And if you're wondering how hot the coil gets during that test, not very. I can still hold on to it with my hands. If I use the infrared thermometer at about 150 Fahrenheit or about 67 Celsius after that short 1 minute. So if you remember at the start of the video I had half a metre of 5mm copper tube, and this is what I made from it. So it's a smaller coil for getting into harder to reach places than with the big coil. It does have fewer turns on it as well, and I will just mention the amount of turns a coil has does affect how well the induction heater will perform. But it's quite an in-depth topic and a bit beyond the scope of this video. Now a question some of you are probably wondering is, what can this induction heater heat up in the way of metals? So I've got a selection of metals here. We've got copper, an aluminium heatsink, a stainless steel bolt, a brass fitting and a standard steel bolt. And I've just got a neodymium magnet here. Now just briefly, how an induction heater works is it's got a alternating magnetic field, and what that essentially means in layman terms is anything a magnet will stick to, this induction heater will be able to heat up. So a magnet we know won't stick to copper, it won't stick to aluminium, it won't stick to brass. It will have a weak attraction to some types of stainless steel. You can see I can just barely pick up the stainless steel bolt, but you can see the steel bolt has a It's actually quite a difficult magnet to get off. It's a very strong attraction, so anything a magnet will stick to that has a good attraction to it, an induction heater will be able to heat up for you. So that wraps it up for this build. Thank you very much for watching. If you found the video useful, please give it a thumbs up, it would be much appreciated. And while you're down there, consider subscribing. It's absolutely 100% free.